Hello, everyone. I'm Norman Wahlberger, and thank you for joining me on this journey into research level mathematics, sort of from an amateur point of view. We're trying to explore polynomial equations. And last time we made some small but interesting progress by kind of looking at the possibility of a power series type of solution. So we are looking at the quadratic equation c0 plus c1x plus c2x squared equals 0 right here. We're trying to solve for x. And we decided to simplify things and replace c0 with just another variable t. And then we were looking for a solution which was a polynomial in t, but rather sort of an extendable polynomial, so sometimes called a power series. So last time we got some interesting numbers coming out, such as what appeared to be Catalan numbers. And what we want to do now is maybe go a little bit further in that direction. So we want to test whether that general direction is extendable. And we want to get a sense of how much more difficult is it if we, expand our view a little bit. So we're going to go through the same computation that we did before, and it's a way of checking that things are working, and we're also able to sort of see how things progress as the level, or in this case, the degree gets bigger, okay? So we're going to replace x now with this expression. It's of degree 9. Let's call all these variables a0 plus a1t plus a2t squared all the way up to a9 times t to the 9. And these a's, these are expressions in the c's ultimately. Okay, that's the aim, is to try to find expressions for each of these a's in terms of the c's, so that when we plug all of this into the original equation, we do actually get 0, at least up to degree 9. So that's sort of what we're doing. Is we're not absolutely stopping at degree 9. We're recognizing that the arithmetic involves terms that go beyond degree 9, but we're just going to truncate. And effectively what that amounts to is this sort of equation that t to the 10 equals 0. Okay, so let's do that. Let's see what happens. So this is a kind of a review of what we did last time, and we'll start down here. Let's say, where are we here? So there's c0 plus c1x, and we said that we were going to replace c0 with t. Okay, and then the x is going to be replaced with this whole thing here. There it is right there. And this thing is going to be replaced also with that same thing. Now, I just remembered that last time I made some definitions. Let's just check what definitions I have. You see, my previous work, I had made these definitions of A1, A2, etc. We don't want to be adopting those right now. So we need to cancel those definitions. That's a really important little check to do in Scientific Workplace. So under compute here, under definitions, there's a little section that gives you some control over definitions. And here we're going to clear all the definitions and just check that there are no more definitions. So A3 really means A3, not something else. Okay, so it runs off the page here. If I make a line break, you can see that, okay, t plus c1 times that plus c2 times that whole thing squared. Okay, great. And I'll put it back up there. And what are we going to do? We are going to, expand this out, and then we want to drop all terms bigger than t to the 10. Now I'm going to try using another feature of Scientific Workplace here. Under the compute section, there's a thing called power series. So let's have a look at power series. And we're going to expand this thing out in number of terms, 9, maybe we'll go 10, and expand in powers of t. Let's see what happens if we do that. Okay, that's great. But you see that the power, these coefficients of, say, t, it's a little bit complicated, but they're not that bad. They've got some brackets in it, but that's fine. Okay, so what we're going to do is we're going to, as before, set this all equal to 0. Okay, and then we want to draw some conclusions from the various equations that we actually have here. The constant term is this thing here. And let's actually just factor that. That's rather special. Okay, and we saw that we've already gotten that last time, so that's equal to this. And so we concluded that, so that a sub 0 was either equal to 0 or a sub 0 equals, what was it, minus c sub 1 over c sub 2. Okay, and we were actually sticking with the a0 equals 0 case. But let's be a little bit more general here because we're trying to see a bigger picture. So let's see what happens if we go more generally. Let's actually write all of these equations together in a big column. So the coefficient of t, coefficient of t squared, nope, sorry, Control Z, that was no good. Control Z. Okay, I think that's all right. Equals 0. And then the coefficient of t cubed equals 0, and t to the 4th equals 0, and t to the 5th equals 0, and to the 6th equals 0, and to the 7 equals 0, and to the 8 equals 0, and to the 9 equals 0. Let's have a stare at these equations for a second. So the first equation allows us to solve for a0, and we've seen that we have these two possibilities. Okay, the second equation, we know what a0 is. Now, so the point is that each of these successive equations is linear in the next a variable. So this one's linear in a2, this one's linear in a3, this one's linear in a4, and the other ingredients are the previous a's and the c's. So we can sort of recursively sort of solve for each of these a's. It's actually completely straightforward. The computer's not doing anything very clever here. Okay, we could do this by hand easily enough if we felt like it. Okay, so let's actually now try to do this. There are these two cases, so I'm going to maybe make a copy of this, just put a copy down here somewhere. Okay, so in this first version, I'm going to actually add the additional condition that a sub 0 is equal to 0. Okay? And now I'm going to ask Scientific Workplace, politely, if it can solve exact. What for? Okay, I have to list all of them. We know what a0, well, no, we don't know what a0 is. Okay, a0, we want to solve for that, for a sub 1, for a sub 2, for a sub 3, for a sub 4, for a sub 5, for a sub 6, for a sub 7, for a sub 8, for a sub 9. Unfortunately, you can't see them all there. Can I expand this thing out? No, I can't expand it out. So I hope I've done that right. We'll soon see if it works out or not. Let's see what happens. Okay, so there's some conditions and there's some sort of special cases, but it's really this that we're interested in. Okay, this is looking all right. So let me put that there and get rid of all of that. So we get a sub 0 equals 0, a sub 1 equals minus 1 over c1, a sub 2 equals minus 1 over c3, etc. Up to, there's a 14 here. And then we get a 42, a 132, a 429, a 1430. Okay, and now I want to just scroll up because I have the previous thing up here somewhere. I want to scroll up and see how that compares with what we got in this smaller case. All right, so if we compare what we got in the smaller case with just 5 terms, say like the A4 minus 5 over C1 to the 7 times C2 cubed. That's exactly the same. A5 is the same. So this extends what we got previously. Okay, so that's good. That means that every time we jack up the number of elements in our power series, what we're getting is an extension of the previous one. So in other words, this part here will sort of stabilize. This initial sequence will stabilize, even if we had, 1,000 terms. The first 5 would always be the same, right? So that there's some sense in which this really is generating a well-defined power series. And the entries now are, okay, up to a minus sign. The coefficients, there's a 0, okay, 1, a 1, a 2, a 5, a 14, a 42, a 132, a 429, and a 1430. So let's copy that, and let's ask ourselves, is this really the Catalan sequence or not? Okay, so we are now going to introduce a very important tool for any kind of amateur investigation in mathematics, or even non-amateur, but especially amateur. We are going to look for the Online Encyclopedia of Integer Sequences, OEIS. And it's the first entry that comes up, the Online Encyclopedia of Integer Sequences, founded in 1964 by Niels Sloan. This is a remarkable site that is so important for all students and lovers of mathematics because it explores the huge richness in integer sequences. So let's enter that list that we copied. 0, 1, 1, 2, 5, 14, 42, 132, 40, 429, 1430. And let's search for it. Sorry, the terms do not match anything in the table. Okay, let's remove that first 0. Start with 1. Let's go for that. Okay, that's better. There we go. The Catalan numbers. Okay, this is sequence A 000108. The Catalan numbers. C of n, and a formula for them. They are like central binomial coefficients with an extra little denominator. So if you look at this formula here, it's 2n factorial divided by n factorial times n plus 1 factorial, both of those in the denominator. Now, if it was just n factorial times n factorial, that would be 2n choose n, the number of ways of choosing n things from 2n things. Okay, and this thing here is 1 over n plus 1 times that sort of central binomial number. You can tell that by scrolling through here. So if you're an amateur mathematician, you can learn so much just by sort of perusing something like this. Just has a wealth of information, maybe too much, okay? But anyway, it's really absolutely a fabulous resource. Look at all this. Look at all these references to the Catalan numbers. They're absolutely hugely important. And of the very many interpretations of them, scroll back up here again, sorry for that. There's probably somewhere the one that's quite important for us, which is in terms of, let's see if I can find where it would be. There's too much information. Okay, I don't know if you can see it all. Anyway, I'm scrolling down here through all this information. Right here. Have a look at this. Here, right here. Whoop, not all of that, just here. So the ordinary generating function, that's what OGF means. C of x equals 1 minus square root of 1 minus 4x over 2 for the Catalan numbers with composite, with another thing. So anyway, that's the thing right there that we want, that little formula. That's an ordinary generating function for the Catalan numbers. 1 minus square root of 1 minus 4x all over 2. So we'll keep that in mind, and we'll go back now to our work in progress. It was c of x equals 1 minus square root of 1 minus 4x, and there was a factor of 2, fraction 2. Actually, let me not write the fraction that way. It's actually nicer, I think, perhaps sometimes to just put the fraction out front. Okay, so 1/2 of 1 minus square root of 1 minus 4x. And let's check that by asking Scientific Workplace to expand that in a power series. Okay, so number of terms, 10, fine. Now we're expanding in terms of x. We get 1, 2, 5, 14, 42, 132, 429, 1430. Sure enough, that's the same sequence. And the next one happens to be 4,862. So in some sense, it's not a surprise. So if you know this crucial fact about the Catalan numbers, that they're somehow related to an expression involving a traditional square root, then it's not a surprise that we're getting it. But it's nice that we're able to obtain this in this way. Okay, so now what we're going to do is we're going to have a look at that second solution, which I remind you comes about by looking at the possibility that A0 equals minus C1 over C2. That was the second possibility. Okay, so I'll put that in there. Let's see what our... No, we still don't have any definitions, so that's good. And now I'm going to solve this thing, but I'm going to solve it for all of these, and I put them up here so I can just copy and paste that into this solve thing. So I'm going to solve, okay, this thing here. I'm going to solve exact, and I'm going to solve for all of these variables. Boom. Okay. Okay. The second one was not necessary. Okay, this is what we're getting. We are getting let's compare that with what we had previously, which was all of this stuff. So this is a more complicated computation, right? Because now A0 is not equal to 0. So if we actually do this by hand, it would be a lot more work because we have to replace all these A0s that are down here with this expression here. There'll be some cancellation, but still it ends up being a little bit, it's certainly different computation than the previous one. But if we compare what we're getting now with what we got in the previous one, there is a difference. There's a difference in the A0. Before we had A0 equals 0. Now we have A0 equals minus C1 over C2. And what about the rest of them? So here this A1 equals 1 over C1, no negative sign. Here this A2 equals 1 over C1 cubed times C2. Same thing as here, but no negative sign. In fact, the same thing appears to be happening all the way through, even to the very end. A sub 9 is this thing, and the previous one was the same thing with a negative sign. So what we may conclude. So we may conclude that we have two possibilities for x. The first one was okay, how should I best do this? Okay, that was the first one. We're starting with 0. So 0 plus, and then minus, that was that one times t. Okay, and t is actually C0. And then minus this one times t squared. Whoops, sorry. That was equal, and there's a t squared there. Haven't messed that up, have I? No, I think not. Okay, and then the next one, this thing here, times t cubed, and then A4 was this one, times t to the 4, and then this one times t to the 5th. So sometimes we have to do things step by step. Okay, we have to be a little bit patient. That's part of the game. That was C5, A6. Okay, here's A7. Have to try not to make mistakes, like I just did there. C, what is that supposed to be? C sub 2 to the 6, and then we're multiplying that by T to the 7. Okay, that was A7 and then A8. T to the 8, and this thing here, T to the 9. So we may conclude that the solutions are, okay, that one, and scroll down here. Whoop. Come back. The other one is the same kind of thing, okay? And to just make it negative, I'm just going to put the whole thing in brackets. Put a negative sign in front of it. Evaluate it. Okay, that was almost the right thing, but we also have to include this minus C1 over C2. Let's just check if that's right. So that's also a series in T, from T all the way up to T to the 9. Where did that go? Oh, the T to the 9 here is here. Okay. T to the 8, T to the 7, T to the 6, T to the 5, T to the 4, T to the cubed, T squared, and T. So let's call these something. Let's call this one X sub 1, and let's call this one X sub 2. And we're going to make this a definition. That's now officially X1, and this one is officially X2. And now we're going to perform some checks, okay? We're going to go back to our original equation, C0 plus C1x plus C2x squared, which we, okay, there it is there. So let me introduce f of x, say, make a definition, but I will put in a t instead. Okay, that's a definition. What are all my definitions? I've got x1, x2, and f of x. The x and the x1 are different. The program recognizes there's not going to be a confusion with those, hopefully. Okay, there's f of x, and now I'm going to calculate f of x sub 1. What happens when we plug this thing into f of x? Simplify. Okay, what is that thing? Well, it's some polynomial in t, but crucially there's a t to the 10 out front. You see this t to the 10 right out front here? Maybe I'll scroll down a little bit. There's a t to the 10 out front, and our assumption is that t to the 10 is sort of working equal to 0. So this is actually equal to 0. In other words, all the lower order terms involved in this expression involving t squared up to t to the 9, they all are killed. So this is really effectively 0 up to level 10. And similarly for x2, we will compute that. Simplify. And again, we see the t to the 10 over here, and that's going to be then equal to 0. So up to degree 10, x1 and x2 really are solutions to the original quadratic, given that t is equal to, what do we say, c sub 0. So maybe we can sort of state our conclusion here, right? We've solved a quadratic equation, a general quadratic equation, in a rather novel way. Okay, so we could maybe even make this a theorem. Let's go to a theorem. There's a theorem. The quadratic equation, okay, we'll write it just like this. Has solutions, and there was x1. Okay, this 0 can be dispensed with. So the quadratic equation t plus c1x plus c2x squared equals 0 has solutions. That expression in x1 up to t to the 9, and the other expression x2 also up to t to the 9, up to degree 9. And because the Catalan numbers are given by this nice polynomial expression, using the formula for the Catalan numbers, maybe c sub n was, what was it? It was 2n factorial divided by n factorial times n plus 1 factorial. And let's just check that. We'll make a definition, and then c sub c of 5, say, what's that going to be? 42. 1, 2, 3, 4, 5. I guess that's the 0th one. 1, 2, 3, 4, 5. And c sub 7 is 429. So we could then, it's relatively simple to write down a formula for these things in general, right? We could write down a power series expression for these two things, and those expressions would involve these binomial coefficients and powers of C1 in the denominator and powers of C2 in the numerator. And of course, t is actually C0. We just changed variables. So there's really a C0 also in the numerator, increasing powers of those. So we could write down a nice formula. And we might start our next investigation by writing down those formulas. And then naturally, seeing if we can jack this up to degree 3. Very exciting. Thanks for listening. I'm Norman Wahlberger.